Hello, in this section we will talk about the compressibility of fluids. We know from experience, if we apply a pressure P, say P1 on a fluid, this will result in a volume V1. And if we increase the pressure P1 to a pressure P2, the volume should decrease to V2. So if we increase the pressure here to P2, which is greater than P1, this will result in a volume V2 that is less than V1. And the changes in volumes is different for different fluids. That's why we need to define a property called the bulk modulus of elasticity. And is defined as dP over minus dV over V. So the change in pressure with respect to a change in volume, and the minus sign here, it means since an increase in pressure will result in a decrease in volume, so that's why we put a negative sign in order to obtain a positive overall value. And this also can be written as dP over d rho over rho. And if we want to prove y minus dV over V is equal to d rho over rho, we can simply say that the density is equal to the mass over volume, and if we differentiate, d rho should be equal to m into minus 1 over V square dV for a constant mass. And if we divide by the density d rho over rho, so we have m over rho into minus 1 over V square dV. And m over rho is simply equal to V, so we will have d rho over rho. V over V square is 1 over V, so we will have minus dV over V. So minus dV over V is equivalent to d rho over rho. And we should know also that an increase in the pressure will result to an increase in the density. So here, that's why we have a plus sign. As units, in the English unit system, the bulk modulus EV has the units of pound force per inch square, or simply PSI, and in the SI unit system it is in a Newton per meter square or in Pascal. We should know that large values of EV means a relatively incompressible fluid. So large values of EV means relatively incompressible fluid. For example, let's take water. So water at 1 atmosphere, if let's say we want to compress it by 1%, or in other terms, delta V over V is equal to minus 0.01. We need to raise the pressure to raise P to 210 atmosphere. Okay, so that is equivalent to delta P equal to 209 atmosphere. So in this case, the bulk modulus is simply 209 over 0.01, so 20,900 atmospheres. So as you can see, we have large value of bulk modulus. So mainly liquids in fluid mechanics applications can be considered as incompressible. Since we need to have large pressure values to have a change in volume, a considerable change in volume. However, if we want to talk about gases, and let's say we have an ideal gas, and we have the ideal gas law as P equal rho RT, and let's say we will have an isothermal compression of this gas. So an isothermal compression, you know that isothermal compression means it is a compression process with T held constant during this compression process. So T should be constant during the compression process, and dP in this case, if we differentiate this equation, dP should be equal to RT d rho, and dP over d rho during this constant temperature process should be equal to RT, and simply RT is equal to P over rho. So that means that the bulk modulus of elasticity for this gas, it is dP over d rho over rho, and dP over d rho is simply P over rho. So P over rho is just simply P. So that means during an isothermal compression, the bulk modulus of elasticity for a gas is equal to its pressure. So let's say, for example, if we take air at 1 atmosphere, that means that the bulk modulus of elasticity is equal to its pressure and is equal to 1 atmosphere. And let's say we want to compress this air by 1%. That means that the change in volume with respect to volume is equal to minus 0.01. And since the ratio dP over minus dV over V is equal to 1, that means that delta P should be equal also to 0.01 atmosphere. So we need to increase the pressure to 1.01 atmosphere. So as you can see, in order to change the volume of air by 1%, we should increase the pressure by 1% also. And that's why if you want to compare the EV for air with respect to EV for water, so we can say that air is approximately 20,000 times as compressible as water. And when dealing with gases, we need to pay great attention to the compressibility effects. So when dealing with gases, we should pay great attention to compressibility effects. I'm not saying that gases should be always considered compressible. In some cases, gases can be incompressible. If the change in pressure is small, you can also consider that the gases as incompressible. So if delta P is small, gases can also be considered as incompressible.